Right. Hello. So what I wanted to do today was do electrochemical cells. So we're going to follow on what we did last time in terms of the basics of redox, which is the meaning of the term reductant, oxidant, reduction, oxidation. Now, were you at the lesson last week, Catherine? I know there were two Catherines there. I just want to check if it was the same one. Yes, great. Okay, so basically this is what you can see here is what we want to do today. So let's look at the first, and the video should come up now. What we want to do is compare strengths of oxidants and reductants to see if a reaction is going to occur. So I'm going to switch these both on, and hopefully you should see two reactions. So we're doing copper sulfate and magnesium in the top one, and magnesium sulfate and copper in the other one. Now, which one is reacting, the top one or the bottom one? The top one. Yep, you can see there's a reaction going. Remember that triangle of observations, or the macro, the micro, and the model. So the macro is all the observations. So you can see there's no change in the bottom one, but there are bubbles. If you did it long enough, you should see that the blue color fades and so on. So if we looked at it, we can write that reaction. The Cu2 plus is from the copper sulfate that causes that blue color, and we've got that magnesium ribbon in there. And what's happening, all that black stuff that's coming down is actually the copper. And I'm going to actually just stop it there. Right, so that black stuff was the copper, and you can see that the magnesium over here is much more pitted. It was nice and shiny there, and it's reacted, it's gone pitted. Whereas, has there been any change in the bottom one with the copper? Has the copper become pitted as though it's been eaten away? No. Okay, so basically we can say there's been no reaction in the second one. And we want to see why the top one has worked, but if there hasn't been in the bottom one. So we'll flip over to the next screen. We can think of copper and magnesium metal in relationship to the electrons. So what I was trying to show here in this diagram is I've got a piece of magnesium metal here in water, okay? And the magnesium is in equilibrium with its electrons. So we're really seeing how strongly does the magnesium hold on to its electrons. So with our magnesium ions, does it strongly hold on to the electrons to form the magnesium, compared to copper ions? Do they hold on more strongly to the electrons to form copper? Now, this is dealt with in quite a bit of detail in 3041, a booklet you'll be doing later. But looking at those diagrams, which one holds onto its electrons more strongly, the copper or the magnesium? Okay, just think of what I'm trying to show here is these 2 plus, those are like the ions. So have I got more ions in solution? In other words, here's my magnesium strip. Do I have lots of ions in solution? So am I going more that way to the magnesium ions compared to the copper? So here I've got my copper metal. Is it, and I've shown all the electrons on the copper. Now, is it losing those electrons very easily to form the copper 2 plus? Okay, just see you typing. So yeah, so the copper is holding on to its electrons stronger. In this equation, I'm trying to show there's a shift more to the copper metal. It doesn't want to go back and lose electrons to form the ions. So there are fewer ions in solution. Now, as I say, we aren't measuring solubility. Like if we put copper metal into solution, are we expecting it to dissolve? It's not quite like that. It's just how more strongly does it hold on to its electrons, or how readily does it lose it. So going back to the terms we looked at last time of reductant and oxidant, which one of those two hands over its electrons more easily? The oxidant or the reductant? So remember, we looked at the ants, happy ant, sad ant. The reductant loses the electrons. That was, remember, the sad ant, the R for its mouth, so it looked sad. So which ones of these would more likely lose the electrons, the magnesium or the copper? Just checking that you've got that, the magnesium. So the magnesium is, can we say, is it a stronger reductant than copper? So by stronger, it's a chemical term we use where it's more likely to do something. Yep. Okay. So this is where we get those ideas of reductant and oxidant from, and we can measure these. I'll explain how we get these measurements later, but if we write these equations down, now notice we've called them reduction potentials because they are always written as a reduction. So remember, oil rig, reduction is gain of electrons. For the rig, reduction is gain. Can you see my magnesium ions are gaining electrons to magnesium? Can you see this is a reduction half reaction? Yep, okay. And the same thing we've done here for the hydrogen ions and the same thing for the copper. And that's why we talk about reduction potentials. Why reduction potentials are not oxidation potentials? It's just the convention. It's just the one they picked. Okay, so when they measure, they always measure it in terms of a reduction half reaction. And again, just an arbitrary thing that they chose, they made hydrogen the reference. So just like we took carbon-12 to be the reference for atomic mass, here we take hydrogen as the reference for the reduction potentials. We just give it an arbitrary value of 0. It's just, we always have to relate things because there's no absolute measurements. So we simply say, if hydrogen is 0, how do the others relate to it? Now, if you look at these values, you'll see the magnesium is negative and the the copper is positive. So we'll explain that just now. But as we can see, if magnesium is a stronger reductant, it actually has a more negative value, and if copper is a weaker reductant, because it holds onto its electrons more strongly and doesn't want to hand them over, it's got a positive value. Okay, so going just back to the equation, and we've had that have happy ant and sad ant. Oh, I meant to ask you this. In this equation, well, obviously if the copper is the oxidant, because it's taking the electrons, the magnesium has to be the reductant. Sorry, I pressed the button too quickly. And if I have the other option, in that reaction, if it was working, what would the copper metal be acting as in that second equation? So in this one over here, what is the copper metal acting as? Reductant or oxidant? As the reductant, because it's supposed to be handing over the electrons, and you can see it doesn't. So it's supposed to be the reductant, and magnesium ions are supposed to be the oxidant, but it's not happening. So what we're trying to say is the more negative the value, the stronger the reductant, and so the more likely something is going to happen. If I have a weaker reductant and a strong so if it's a weaker reductant, and it does mean that the oxidant would also be weaker as well, it doesn't work. It's like saying putting a let me just do it in the next. Okay, so before I go into the next page, if I have the stronger oxidant, because if copper ions is a weaker reductant, can you see it'll be a stronger oxidant? It's the opposite. Weaker, stronger, and oxidant reductants. And do you notice when we write these reduction half equations, we always have the one reactant on the right-hand side of the equation, and the other one on the left-hand side, if we write them as reduction half reactions. You can't have magnesium ions reacting with copper ions. It's not going to work because you need one to hand over the electrons. So in this case, it's magnesium handing over the electrons to go that way, and the copper is taking those electrons to go from left to right. So one reaction will always go from right to left, and the other one will always go from left to right. So you get given a table like this, and this is an image I was trying to think of. If this is the weaker oxidant, it is not going to be able to take electrons from a stronger oxidant. So you need always a stronger oxidant reacting with a stronger reductant. Now this is a table that's on page 40, and it's of your CH3000, and it's also in your later on, I think, towards the end of the booklet as well. Now these figures are most probably too small for you to see, but notice that it sort of starts from a very negative value, -3 point something, and it gets more and more positive, and it goes down to a positive 2.87. There's only some of the reduction potentials that you can get in here. Notice that at the bottom, fluorine is the strongest oxidant. Now, what do you know about fluorine? I did mention it last time when I was comparing oxidation numbers, and I said something about oxygen and fluorine. That's correct, Michael. Fluorine's the most electronegative. So do you think it's holding on to its electrons the strongest, the hardest, or will it easily give up its electrons? It'll hold on to it tight. So can you see it's the strongest oxidant? It does not want to give its electrons away, and if anything, it'll grab them from somewhere else. Okay, so think of that if you're trying to work out which one's the strongest and the weakest. Fluorine is always the strongest oxidant. It'll hold on most tightly. It's the most electronegative. Lithium, on the other hand, lithium metal, so we're looking at the other side, is the strongest reductant. And that's why if you think of all the batteries you use, perhaps for your cell phone, for your any of the other ones, in the old days you always got the carbon battery. Now they're mainly lithium batteries. If you think of what batteries do you use in your laptop, if you have one, or your tablet, or your in your phone, do you know what battery you have? Is it a lithium? Okay, it's most probably a lithium battery. I know there was something on Stuff News the other day where a child had swallowed a lithium battery, and because it was such a strong reductant, it sort of corroded through and damaged the child's stomach and esophagus, and it was a bit horrendous. But lithium is used a lot because it's at the top of the table. It's most likely going to give its electrons away. So if you pair lithium up here with something down over here, there's a big change in potential. So one is very readily handling over its electrons, the other one's very readily grabbing electrons, and so you get a very big voltage. So if you want a good voltage, then you want a number from up here combined with another number down there. But more of that later. Okay, any questions so far? So you got it clear in your head about how these reduction potentials work. You've got the more electronegative elements down here that want to hold onto the electrons are strong oxidants, whereas on the other side are the strong reductants up there. Okay, I see Michael is typing. So very quickly, let's see how much you know, or we've got these two reactions going, and see which one is reacting. So we're adding colorless solutions to both of them. So colorless solutions are being added to both. Where is the reaction happening? The top one or the bottom one? And I'm just going to stop these while it's in the bottom one. Can you see we had a colorless solution going into a colorless solution down here, and it's become brown, whereas this one was orange. This one is orange, and as you added a colorless solution, it looks as though it's faded, but that's just because it's been diluted. Okay, so what we've got here is really bromine water, so it's bromine in solution, and I've added colorless chloride to it, and there's been no change, whereas here I've had chlorine water, so it's chlorine in here. I've added colorless bromide to it, and this, I hope you know, if you look at the two colors, it's bromine, aqueous bromine, and then I formed colorless chloride. Okay, so looking at these values, so the bromine to bromide reduction potential, if bromine gains electrons, is a positive value of 1.07, and the chlorine reduction potential to form chloride is 1.36. Which one of those is the stronger, I'm just wondering what would be the easiest one to say, the stronger oxidant? So this is the one that's going to grab electrons from the other, the Cl. Because remember, the more positive the value, the stronger the oxidant. Think of fluorine, the most electronegative, where it sits. And we can show that with this. So chlorine here, in this equation, think of oxidation numbers that we learned last time. Is the chlorine acting as an oxidant or a reductant? We're going from an oxidation number of 0 in chlorine to an oxidation number of -1 in chloride. So it's going from 0 to -1. Has it gained or lost electrons? Correct, Catherine, it is the oxidant, because the oxidant, think of that's happy ant, it's gained electrons. Sorry, I meant to show that. And so that's the oxidant, and the bromide must be the reductant. And of course, if I did it the other way, if that reaction had to work, the bromine would have to be the reductant, and it is a weaker reductant, because if I look at the values, bromine is a weaker reductant. Well, if anything, bromine won't give its electrons away. It's a very weak reductant, because if bromine gave its electrons away, it would form a positive value, and it doesn't want to do that very readily. I haven't actually shown the E0 values of if it gave away. But you can see that the chlorine is the stronger reductant. And again, our two reactants must be on opposite sides. So the bromine is on the right-hand side. It is losing electrons to form bromine, and the chlorine is on the left-hand side. It's gaining electrons to form chloride. Okay. So what I'm going to show here is how we measure that reduction potential. So remember, I said we use hydrogen as our reference electrode. So this just sort of shows various standard conditions. I just lifted this off YouTube. So this is my hydrogen electrode, and I'm comparing it with the zinc. That's a zinc metal in a zinc solution. And do you notice my conditions? I've got to have zinc ions as being 1 mole per liter. I have to have my hydrogen that's being bubbled through at 1 atmosphere pressure, and my acid in here must be at a concentration of 1 mole per liter. Those are what we call standard conditions. The temperature has to be 25 degrees as well. That's another standard condition. And if you did that, and I'll just stop it there, if you had it under the standard conditions, then connecting a voltmeter up to it, you would get a value of 0.76. And I'm just going to go back a bit. So if we put a voltmeter in here, that comes as a positive value, but what we find is we want always hydrogen to act as a reduction. So if we add hydrogen gas through here and it goes to the hydrogen ions, is the hydrogen gas being reduced? Is it gaining electrons? No. So if the reaction works the opposite way, then we simply say, so, and I'll just go move forward to, okay, I'll have to, there, okay, right. So if the reaction works the opposite way, so in other words, it's the zinc that's gaining electrons, then we give it a negative value. Because if the zinc's gaining electrons, the hydrogen must lose the electrons. And remember, we want to have hydrogen as a reduction potential, so it means this has had to work opposite. So this is how we measure it. We just compare to the hydrogen electrode. If hydrogen is acting in a reduction half reaction, the other side gets given a positive value. If we've had to force hydrogen to go the opposite way, then the value is given a negative. So this is just the way it works. And here's the same thing. Oops, sorry. Yeah, that'll go now. This is now copper. So here we've got the hydrogen electrode. The same sort of thing as platinum over here, because we need to have a solid electrode for the electrons to go through. It has to be in, remember, 1 mole per liter acid. In this case, it's hydrochloric acid. Here's our hydrogen gas. Remember, we have to have hydrogen gas going through, bubbling through at 1 atmosphere pressure. So this is just what they're showing. Here it's bubbling through over the electrode, and the solution is hydrogen. And we're comparing the copper sulfate. It's got to be 1 mole per liter. I'll explain this bit of paper a little bit later on. And when we compare the reading we get here, oh, don't worry about that, I'll explain that now. Okay, I'll stop it here. Can you see the reading there? Is it big enough to see? Is it a positive or a negative value? It's a positive value. You know, by the way, if you were doing this practically the way you connected it up, which way the reaction is going. Unfortunately, we can only show with the YouTube clips. So this is showing that in this case, the hydrogen ions are gaining the electrons to form hydrogen gas, and my copper is, so if the hydrogen is being reduced, the copper is being oxidized. Okay. So when we work out the values of copper compared to hydrogen and zinc compared to hydrogen, we can then take copper and zinc together and hook them up in the same way. So I'll just show what happens here. I really just want you to see the reading, because we're going to be talking about that reading. So we've got here zinc and zinc sulfate, or any sort of zinc solution. It has to be a soluble zinc salt. Sorry about that. And then we've got a piece of copper in copper solution. Now again, I'll be talking about that piece of paper, or we need something just to connect the circuit. And so because the circuit is incomplete, there's no value. But now that completes the circuit. I'll talk about that now. It says there's salt bridge, and we'll talk about that. And can you see the reading there of 1.22? And just bear that in mind, because we'll come across that very soon. Okay, any questions so far? I've gone through that quite quickly. Right, you're good. Okay, so you saw the setup, and I said I'd talk about the salt bridge and so on. So this is a schematic diagram showing what we've got. So we've got zinc sulfate at 1 mole per liter, zinc plate, and then some sort of either a light bulb showing electricity is going through there, or a voltmeter, as you saw that yellow voltmeter, with a copper plate and the copper solution. But we need to have a complete circuit, and that is the point of the salt bridge. Really what the salt bridge is, some sort of connection where you can get a solution of ions moving through. So if you have a bit of filter paper that's soaked in potassium nitrate, I don't know if you saw that came up as potassium nitrate in that one video. Potassium nitrate consists of potassium ions and nitrate ions. Those ions are free to move in solution, and so that will complete the circuit. So electrons are going through the wire to there, and we've got ions going through this bit. Because can you see, if we've got electrons going through here, I'm going to get more and more zinc ions going into the solution. So what can you tell me is happening in this solution? Is it becoming more positive? Because those electrons are going along up there. So thinking about what's happening, is my zinc solution becoming more positive? Yes. And if I don't fix that, the reaction is going to stop, because you're not going to get more positive ions being formed and leaving the zinc to go into a positive solution. It won't do that. It would rather stay where it is. So what happens to try and make this neutral? We have then anions moving through here to make this neutral. The same thing over here. We've got the electrons coming through over here. My copper ions near this copper plate are picking up those electrons because it's rich in electrons, so it grabs them and deposits onto that copper metal. So we've got our copper ions grabbing onto the electrons to form copper metal. So we're getting more and more copper metal being formed. But what can you tell me about my solution? Is it becoming more positive, more negative, or staying neutral? So nobody's having, okay, Catherine, you having a go? More negative. Because remember, this is copper sulfate. So if I had, say, 20 copper ions and 20 sulfate ions originally, I mean, it'll obviously be thousands more, but let's just pick small figures. If 10 of those copper ions have plated onto the copper metal, I'm left with 20 sulfate ions and only 10 copper. So overall, the solution is going to be more negative. So again, the reaction will stop if I don't fix it, because no more copper is going to go to this electron-rich copper plate, because it's more rich in electrons in the solution, because it's so negative. So when the anions go over there, and any cations we've got here will migrate across as well. So this is soaked in, say, something like potassium nitrate. So in the beginning, you're going to have the potassium ions go down there and the nitrate ions moving across here. And eventually, as I say, you may get enough zinc moving across. Often the reaction is stopped by then. Okay, so here I'm trying to show it in small, closer detail. And I've shown the salt bridge like this. So if I had copper sulfate, the sulfate ions are moving through there. The zinc ions would move through there. The copper is plating onto the copper metal. So I'm trying to show the copper ion grabbing electrons and has gained extra 2 electrons. Whereas here the zinc metal, which had its 2 electrons, is now becoming a zinc ion, and those electrons are being sent up there. Okay, now I've put some labels on here: anode negative and cathode positive. These are one of the things you have to learn. Cations always go to cathode, and I think I'll put it there. So think of cat and cat. Cations go to cathode. So if my copper ions are depositing on here, this must be the cathode. And you're sort of wondering, why are copper ions going to a positive species? That's really because the electrons from the zinc, remember the zinc is rich in electrons, it gives away its electrons more easily, so it's negative, and those electrons then move to a place which wants to grab those electrons, which is copper. So it's really because it's negative from the zinc and the electrons are moving to the copper over there. Okay, so what we can think of is we've got an equilibrium. Zinc is losing the electrons, copper is gaining, so we've got this sort of flow around, okay, and the zinc is a stronger reductant because it's got a more negative value, and the copper ions is a stronger oxidant because it's got a positive value. Now we don't want to always keep on drawing those. If I just go back, so I'm just going to go back to the previous one. We don't always want to draw cells like this. This is what we call an electrochemical cell or a galvanic cell. One actually point, do any of you go onto YouTube and look at, say, chemistry videos on YouTube? Sometimes, okay. Just a point about the term electrochemical. Pretty much the rest of the world uses the term electrochemical for both types of cells. A cell that gives off electricity, as this one does, I haven't really spoken about that yet, and a cell that needs electricity to work. So they use electrical as an overall term, and then they say, right, the one that gives off electricity we call a galvanic cell, and the one that needs electricity is called an electrolytic cell. We'll deal with that next week. New Zealand, however, and the way they use the terms, particularly in the standard, they use electrochemical cell to mean giving electricity only, not the other one. So if you're watching or you're reading some books that are published in another country, just be aware of that sort of possible confusion. New Zealand uses it very specifically. It's much broader in other countries. Okay, sort of going back, we don't want to keep on drawing this out in detail like this. It would take ages, say in the exams, drawing this. So what we do is we have what we call a conventional cell diagram. This little thing here represents what you saw in the previous slide. So what we're showing is zinc going to zinc ions. So we're saying zinc going to zinc ions and copper ions going to copper metal. So it's always written from the reaction going from left to right. So we're writing that way, zinc to zinc ions and copper ions to copper. A few things to note about these. Where are the solids? Are the solids sort of always on the left-hand side? Are the solids on the two outermost points? Are they on the two innermost? Right. Catherine, they're on the outside. Zinc is a solid. That is a solution. That's a solution. That's a solid. The two outside bits have to be solids. So if you, for instance, got a reaction like that bromine one and chlorine, were there any solids in that reaction? Mixing chloride with bromine? No. So you have to add a solid electrode to that, and it's normally platinum because that's the most unreactive metal. Sometimes we use carbon because it's cheaper. Platinum is expensive. Did you notice in that hydrogen electrode, where it's hydrogen gas going to hydrogen ions, what solid electrode did we have there? Do you remember seeing that little square bit of metal? Or sometimes it's a bit of wire. Can't remember. Okay, it was a piece of platinum. Okay, so you've got to have solids on the outside. And when you change a phase, so this is going from zinc to zinc ions, we're going from a solid to a solution, we use a vertical line. So here we've got copper solution going to a copper solid, changing from aqueous to solid, so it's a vertical line. And then in between my two reactions, remember this is the what? The reduction or the oxidation, if I go from zinc to zinc ions. Does anybody want to have a go? It's either oxidation or reduction. Which one do you think it is? Zinc to zinc ions. Think of oil rig. Anybody? No, okay, right. If I'm going from zinc to zinc ions, I've lost electrons. Oxidation is loss of electrons, so that would be an oxidation. Okay, and let me just do the other one. The other side will be a reduction. Now, one way you can think of it, we always read in English from left to right, so you can think of O comes before R, so the oxidation must be written for the reduction. The other way to remember is oxidation has an A in there before the shin, okay? So the A stands for anode. Oxidation occurs at the anode, and reduction, there's a C before the shin, reduction occurs at the cathode. So those are two ways you can remember how we write the cell diagram. Okay, oxidation on the left because O comes before R, and then you'll know that this Cu is at the cathode or the anode. Think of this tip over here we had. What letter comes just before the shin? The cathode. And this zinc is it the cathode or the anode? The anode. Great. Okay, so those are just little memory aids to help you. Okay, the other way is two little pictures if you're a visual learner. Okay, I was thinking of a red cat, and I've noticed the positive pluses for the eyes and so on to help you think of the cathode as positive. So reduction occurs at the cathode, red cat, reduction at the cathode, or anox, the anode has oxidation. And I've tried to make a negative sign by the eyes and a negative sign over there, so you'll remember that it's negative. Okay, any questions so far? No? Okay, so going over the rules, because you have to be able to know them. First of all, we know the oxidation is on the left-hand side and the reduction is on the right-hand side. So remember that O is before R, so oxidation, reduction. Okay, and we had that A for, and then the C for the cathode. Okay, the vertical line separates them different states. So if I have, for instance, here is where I've got platinum solid going to, what form is hydrogen in? Solid, liquid, gas, aqueous. Gas. So I'm changing from solid to gas, so I have to have a vertical line. And if I go from, sorry, my cursor disappears. If I go from the gas to aqueous, another vertical line. The double line we'll talk about just now, but you know about that. What does a double line represent? So Catherine's typing. It's the division between the oxidation reduction, and it represents the salt bridge, because the salt bridge is the one that connects the oxidation half reaction to the reduction half reaction. Without the salt bridge, nothing's going to happen. So we have to have a salt bridge. And then, of course, this is an aqueous going to a solid, so we have another vertical line. If we have two things in the same state, so we haven't had an example of that yet because we've had bromide to bromine, although you can get bromine water, so that's an aqueous as well. But take this example where I've got, say, iron 2 plus going to iron 3 plus. So I'm oxidizing Fe2 plus. They're both in solution. They're both aqueous. So if I have something in the same state, I use a comma. So both of these are aqueous, so I don't draw a solid line, I use a comma instead. Solid going to aqueous, so straight line. Now I'm changing a salt bridge, so two double lines, and aqueous to solid, a single line. Okay, and then as I've said, the double vertical lines are always a salt bridge. They have to be there, because without it, it's not going to work. Okay, and then we did point out that your ends have to be solid. So if you say, just ignore this PT, if I just had hydrogen going to hydrogen ions, I don't have a solid here, so I have to add a solid electrode. It's just because electrons have to have a place to go. Electrons are not going to move through a solution or through a gas. So we need solid. It's usually a metal, although it doesn't have to be a metal. If we have to add an electrode, though, it'll always be platinum and, as I say, sometimes carbon. You may just have C here instead. So, but you'll see I've got my two solids there, and again I've got two solids there, platinum and copper. Okay, and then we've said the platinum is used. It's added. It's an inert electrode, so it doesn't take part in the reaction. It's just a means for to conduct the electrons along. Okay, right. Now I want you to have a go. Can you see if you can write the cell diagrams for those four? So start with the first one. It's very similar to the copper zinc. We're just using copper and magnesium. So Michael and Catherine, if you'd like to have a go, just use a backslash on your computer just to make the vertical line. So remember oxidation first, so you must think of the stronger reductant, the one that's giving off the electrons is the one that's in the oxidation. So Catherine's having a go. Right, so copper going to copper 2+, and then fine, you made it horizontal, but that's fine, you got the right idea. Correct. Okay, you would just, instead of course having a horizontal line, you'd have a vertical line, but you've got the right idea. So there you go. Now what I've done is I've emphasized the change in state, so I've put in the solid, the aqueous, the solid. So you can see that. At level 3 it might be a good idea to do that. When you start off, leave them out so you can sort of clearly see the pattern, because this makes it a lot more fussy looking. But once you're used to writing cell diagrams, just put in the states as well. Does anybody want to have a go at the second one? Now you can either decide this is a gas and that's an aqueous, or you can decide that, remember that in that thing we added actually chlorine water, so you could actually put in a comma there, because you can assume that it was an aqueous solution of chlorine and we're forming an aqueous solution of bromine. Does anybody want to have a go? Michael, do you want to have a try? Okay, not a problem. Why I'm just doing it because then I can perhaps see if you do something a little bit different, then I can try and work out, you know, what an issue you might have, and then I can hopefully get you on the right track. Okay, I don't want to use up too much time for this, so let's just go through it. Now, I've done it, I've chosen it to have it, because the video showed it as bromine water and chlorine water, I've chosen to make it both aqueous, and because I don't have a solid, I had to add a solid. And because there's no solid on this end either, I've had to add a solid over here too. So platinum is in both cases. And I've made both of them aqueous, so I've used comma. But if you had put a straight line and made one gas and one aqueous, that's fine. And this one's pretty much the same. The hydrogen has got no solid, and that's why I've had to add the platinum. But otherwise this is exactly the same as what you had up there for the magnesium. And finally the last one, it looks very clunky and you go, wow, you simply can leave out the other bits. The important bit is the dichromate going to chromium ions and the sulfur dioxide going to the sulfate ions. This is a reaction you saw in that last video or that last one we did. So again, there's no solids in this reaction, so we've had to add platinum electrodes on each end. So it's SO2 gas, because we were bubbling the gas through to form sulfate, and the aqueous dichromate forming aqueous chromium with a comma. That's about really the hardest sort of cell diagram you'd get, really, that you'd have to work out. So, as I say, this is being recorded, so hopefully you can look at it again. And if you can finally do this, then you aren't going to get anything harder. And actually, the task is not hard. Okay, in the final 15 minutes, I want to just go through the cell potentials, because I was talking about, remember the lithium battery, you wanted that big change in voltage to get a good battery. And so we can use the standard cell potentials to work out if a reaction is going to happen or not. And the way we do it is we say the voltage of the cell is, if we take the reduction potential of the reduction half reaction and the reduction potential of the oxidation half reaction, and well, subtract that from there, if we get an answer that's positive, the reaction is going to work. If we get a reaction cell voltage that's negative, the reaction will not work. So let's take the copper zinc one we were looking at. Okay, so instead of say giving you as those reduction equations, you'll find it's just been shortened to a couple, as in Cu2 plus is coupled with Cu, so you can write your own reduction half equation from those two bits, and it's 0.34 volts. Here's the other couple, or think of the reduction potential as zinc 2 plus going to zinc. You see, it's always done as a reduction. It's got to gain electrons to get to the other side. And that is its value. Remember, we got those values when we compared it. And this is then what we then do. E cell is the reduction potential of the reduction half reaction. Now, which is the reduction half reaction? This zinc to zinc ions, or the copper to copper, copper ions to copper? The copper. So we have to take the value from the copper, that's the reduction, 0.34, and then we have to take the value for the oxidation, so the minus 7.6. So 0.34 volts, subtract, you always subtract, and you just take the value as given, negative 0.76, and we get a positive value. So if it's a positive value, will this reaction happen? Yes, and we say it's spontaneous, and so a reaction is going to happen, those electrons are going to move, and we're going to have a cell that gives off electricity. So it'll be an electrochemical or a galvanic cell, it will give off electricity. I just wanted to see if there was something else to note. No, okay, well, we'll do some more examples. So if we had something like these cell potentials, I've done it either as cell diagrams over here or as reactions. Would those cells work, or would those reactions work? We can find out by using our values. Now, the values will always be given. Oh, okay, well, let me do this first. I just suddenly realized another thing I wanted to say. Let's do this one. So the E cell is, remember, the reduction, subtract the oxidation. This side is the oxidation, so I've got to find the magnesium. Okay, goes under the oxidation part. The reduction must be the copper, so it's 0.34. So 0.34 subtract negative 2.36 gives you a positive value. So will the cell generate electricity? Yes. Okay. Do any of you want to have a go and just work out this particular one? You're going to need the bromine value and the chlorine value. So if you've got your calculator handy, so Catherine is typing. Okay, right. There you go. Oh, don't forget. I have made a mistake. Sorry, and I have made a mistake. I added them. You are quite correct, Catherine. It's not 2.43, it's 1.36 subtract 1.07, as Catherine rightly pointed out. I made this a negative value, and that's why I got a big thing here. It's 0.29. Do you get 0.29? If you did it in your head, okay, 0.29 volts. But it's still a positive value, so it'll still work. Okay. If we did this one, then it's, again, the hydrogen is being gaining electrons, and the magnesium is losing electrons. So hydrogen, of course, is 0, and I subtract the magnesium value. So if I put magnesium metal in acid, if you did a level 1 reaction where you put magnesium in, say, tartaric acid, it fizzes away. It shows that reaction is spontaneous. Magnesium will react in acid, and it will give off, that reaction will work because it's got a positive E0 value. And finally, this other one that we had, we know it's going to work because we looked at that reaction, and if we use those values, you can see it's also positive. Now, just a point I want to point out is those E0 values are, remember, they're under standard conditions. So when a battery runs flat, okay, it's because the conditions are changing. So can you see, if I had 1 mole per liter of dichromate, as this reaction is happening, do I still keep on having a solution of 1 mole per liter concentration? No. So as this dichromate decreases in terms of concentration, this is also decreasing in terms of concentration. My standard conditions are changing, and what basically happens when the battery runs flat, this voltage gets less and less and less, because it's, these values are changing because it's not under standard conditions anymore, until the voltage is so low that nothing happens. Once the voltage reaches 0, it's definitely stopped, but normally it just has to drop not very much, and then the resistance in the cell is just too much, and that'll just stop from the ions and the electrons moving. Okay, so if you think back to that cell we had shown in that YouTube clip, we worked out as copper zinc cells should have a standard E0 value of 0.34. If you watch that video again, it was something like 0.22 volts. Sorry, the overall was 1.10, and it was actually a different value. If it's different to this calculated value, is that cell done under standard conditions? No. And you'll see some of my diagrams actually, or some of my photos in that 3072 book, it's not quite right, and that's because by the time we'd done the photo and so on, the concentration had changed, so it didn't show the same voltage. So just very quickly as a summary in the last 5 minutes, okay, an electrochemical cell uses chemical energy to produce electrical energy, so it's producing energy. It's what we call a spontaneous reaction. In other words, that reaction can happen. Later on you'll learn about sort of kinetics. There are other things that can stop it from happening, like what I said with your battery. Once the voltage has dropped too much, even though it might still be a positive voltage, it's not doing anything because there's too much resistance. So, but we still would consider it to be a spontaneous reaction. The E0 cell value has to be positive when you calculate it. It's got a positive cathode and a negative anode. So that is one thing you have to remember. Reduction occurs at the cathode. Remember that thing of reduction, the C before the shin stands for cathode as a type of mnemonic aid, and the A in front of shin of oxidation is for the anode. And then, of course, we can represent it via a cell diagram. So we don't have to draw out all the beakers and everything. And that's pretty much it. I don't think I've got anything more. No. So, any questions? You think you're fine, right. Now you'll find in the booklet there's a lot of extra things. I've given you examples of non-standard conditions, and I've given you other things to do, and it's what I've done on this lesson are the important points. If you can do this, you should get excellence. Okay, I mean there's still one more lesson to go. So these are the important bits. The other bits are to explain and give the background and give all the extra detail, just to sort of flesh it out a bit. So next week we'll look at electrolytic cells, the opposite of these, the ones that use electrical energy to produce chemical energy. So you think of a battery. When you've got a battery, it gives off energy, but when you recharge it, is it still an electrochemical cell? Was it still a galvanic cell when we're recharging that battery? No, it's not. When it's only a galvanic cell or electrochemical cell when it's giving out electricity, but when we're recharging a battery, we are putting in electricity, and we're doing a chemical reaction by adding in that electricity. So that's what we'll look at next week, and then we'll compare the two, because that's what the task is. You've got to compare the two types of cells, and we'll look at some uses, so like rechargeable batteries. That shows both aspects. Okay. Right. Well, if there aren't any questions, we can stop now, and I'll download this. I'll send out the link next week, and I'll have it on Ottle as well. If you've got anything that you'd like me to answer questions, or I'm trying PowerPoints. Before last year I didn't use PowerPoints because I'm not too sure if you have a death by PowerPoint. Do you find this way of this sort of lesson, is this okay? You're not sort of getting death by PowerPoint. Okay, that's okay. And Michael, I know you said you're not sure. Have a look at it and see how you go. I mean, that's why I'm also putting it on YouTube and give you the recording as well. Okay. Okay, Michael's starting run. Okay. Have any of you looked at the recording of the other one before this lesson? Or you found last week's lesson? Okay, so you found last week's lesson was okay. It's not too big a gap. Okay, Catherine, you did look at it. Okay. Right. Well, see you next week, and I hope you have a good weekend coming up. I know it's only Thursday. Right. Bye.